Hey folks, day two for us here, all right? So what you're seeing now is this is the start of day two lecture for us. I'm going to walk you through some of the stuff with day two here. We're going to do what's called baby kinematics, and I'll explain that here in a second as we get there. We're also going to talk some 1D motion, and then I want to just clarify some lab 1-2 stuff that I didn't do a good job with yesterday. So I do want to apologize. The amount of clarity that I had and the issues that came up because of that, I didn't anticipate those. I'm sorry about that. Hopefully today will be a better set of notes, and email and everything like that will be a lot more clear for you. So here we go. All right. Kinematics and stuff like that. All right. Let me get this going here. There we go. Okay. Just some tidbits for you to look at here, okay? What you're going to see here is that font color is very descriptive for me. Um, Typically, white font is something that I want you to write down. So when you're looking at the notes and you see white font, that usually means it's important enough for me that I want you to have that in your notes or something to that effect. All right. Yellow font, hey, just think about it. Read it through, look at it, see what it says, and then after that, just kind of check out and mentally process it. It's not going to be something that I'm going to test you on, but it is something that is at least interesting or will add to the point there. Red fonts are big because that's quiz, that's tests, that's topics, that's dates, that's stuff that you need to just be aware of because those are important pieces as well. You don't have to necessarily write them down unless you're using a planner or a calendar or something like that. But otherwise, those are kind of the things that will help you as you get through this stuff. All right. So here we go. Let's do some physics now. All right. So we start off with this question of 1D motion. We want to know, what does 1D mean? We often hear about 3D, right? Meaning that that's kind of the latest craze as far as game is making it virtual, making it augmented reality, doing stuff like that. So we go back and say, well, what does 1D mean? Well, for us, 1D means one direction, not the band. I know, right? But just a single direction. So it's either left and right. So from your left side to your right side, it's up and down. So we're working kind of that y-axis, so to speak, or it's in and out, in and out. That's that z-axis, all right? So as we start this course, as we start these notes, as we start the physics education for you, what we're going to see is that 1D motion really just limits the number of variables we have. And we just see, okay, it's moving from the left side to the right side, so to speak, all right? That really becomes important for us because it eliminates a lot of the other variables that we have to worry about later in the year. Okay. Distance and displacement used to really push us really hard. But as I've started to understand it more and understand the difference more and really understand kind of the confusion that sometimes this creates, we really just push for distance. Now, that doesn't mean that displacement's not important. Displacement is described as a change in position and depends on the starting and ending point. So think about this with displacement, all right? If you were to go out to a local track, right? And you were to start on the starting line, run one complete lap, and end up back on that finish line starting line. Your displacement in that case would be the difference between your start and your end point, which would be 0. If you think about your bed in the morning, right? Once you crawl out of bed, 12 hours, 15 hours, once you go back to that bed, your displacement is going to be 0, okay? Now, displacement is good. It helps us with some stuff. But like I said before, distance really is important. Now notice the white font, okay? Distance is the measurement of the path actually taken. So if we were to take your steps, right? So if we put a pedometer on your hip or used your health app on your phone and see how many steps did you take, that would measure the distance. It'd be really weird if all of a sudden, like a gas tank in a car measured displacement. Think about that, right? You got 5 gallons of gas at your house. So you drive all over the place. As long as you drive back to your house, you'll never lose that 5 gallons of gas. Yes, it may be based on your range a little bit, but at the same point, once you get back there, you don't have to fill it up again. That would be so awesome. But that's not how our gas gauge works, right? That's not how fuel in our vehicles work. You get a set distance, 100, 200, 300, 400 miles. Once you drive that, guess what? You run out of gas, you're done with that thing, okay? Distance for us is substantially more important, okay? Kinematics now, all right? We made a little bit of a different decision this year to run through what we call baby kinematics and save some of the bigger kinematics for just a little bit later in the year to allow your math to catch up with you. Okay, so kinematics, as you can see, is a subfield developed in classical mechanics. It describes the motion points, bodies, and systems without considering the forces that may cause them. So really for us, kinematics becomes this study of movement, of motion, but we just are going to measure that motion and that movement. We're not actually going to apply forces to it. Meaning, if you push on a vehicle, that's going to apply a force. It's also going to cause it to move a certain speed or a distance. We don't, at least at this stage, care about how much force we put on it. We just care about the distance and the time it takes to travel on that thing. Okay? So, when using distance, we don't want to write out the word distance every time. So we start to use variables. Distance is represented by the letter d, lowercase d. Okay? Now, we can also measure displacement that way, but for us, because distance becomes important, that becomes the one that we're going to really use a lot of, all right? Measurements for distance units are, so think about how you measure length, a height, a width, something like that, right? So it can be meters, it can be centimeters, it can be kilometers, right? It can be inches, it can be feet, it can be miles, all right? You go out into space, we're not necessarily going to measure stuff in meters. It could be astronomical units. It could be light years. It could be parsecs, right? Back in the day, they used to measure horses in hands, right? It could be cubits, all right? All of those become different measurement units that we can use. Now, to be fair, the one that we most often use is meters or centimeters, all right? Now, a lot of us, though, may not be real aware of that, so we may now start to look at stuff in feet and inches, all right? Either one, absolutely fine. So we ask, what happens if the object moves? A change in distance is represented by delta d. That's that triangle d. Triangle means change for us. Okay? So if we change our distance, so if I go here to 200 feet away, my delta d would be 200 feet. If I ran, a kilometer, my change in distance would be 1 kilometer, 1,000 meters. Okay? This is what we'll use more often than just the variable of d, because we're not going to say, hey, 1,000 feet. That doesn't do a lot for us. Like, what happens at 1,000 feet? Oh, you moved to it, or you slowed down to it, or what did you do to get to that 1,000 feet? That becomes important for us. So then we say, what if the object changes distance now? Now, we obviously know that this is delta d, but what we can do is start to say, well, what happens if it changes horizontally? Now, question becomes, that horizontal axis, what do we call that? You're right, that's a delta x, right? Vertically, up and down, dy. In and out, that's going to be dz, all right? Notice by putting a subscript there, by putting a letter after it, below it, what we start to do is we start to be able to label directionality on this. We can say, hey, it went 100 feet to the left. All right, perfect, that's dx. This becomes incredibly important for us because it allows us to break down movement into one dimension only. We don't have to yet worry about if we do something like a projectile motion, right? Launching a bullet, throwing a ball, going off a jump, right? If we go off a jump, there's two components to it. There's an x, the horizontal, and there's a y. For us in the world of physics, that becomes a multi-layered problem, because it becomes really difficult, because we have to consider the x and we have to consider the y. All right, that one becomes really challenging. We're not going to do that yet. Okay. So when an object moves, if it has speed, speed is a raw number. I'm driving 60 miles an hour. Well, how fast am I going? 60 miles an hour. At that moment in time, I'm going 60. Oh, I went up to 70. Okay, well, I'm going 70. Right? If you ever drive into a construction zone around here and they got the big speed limit signs and they show that speed blinking on you, or if you're ever on Flagstaff over by Farmington around the roundabout there, they got blinking signs that say, hey, how fast are you going in reference to 30 miles an hour? That's just speed. It says, hey, I'm going 35. Hey, I'm going 36. Hey, I'm going 30, right? When we measure this now, for us, our common one is meters or miles per hour, MPHs, right? We'll also see the metric equivalent of that, kilometers per hour. We'll use meters per second. Sometimes you'll hear feet per second, right? Velocity is another way that we can measure how fast something moves. Now, the difference with velocity and speed is velocity is a direction, meaning it tells us which way this is going. So if we were to say, all right, you're going to go out on Highway 35. right? You're going to drive the speed limit until you get to Iowa. Speed limit on Highway 35 is 70 miles an hour. That's the speed. The velocity that you're going to have to drive is 70 miles per hour south. Now, can you drive 70 miles per hour north and get to Iowa? Yes, you can. But you're going to have to go around the Arctic Circle, down the other side, and then back up through South America and everything like that. It's going to be super painful. Instead of about a 2-hour trip, it's going to be a 2-day, 5-day, 10-day trip, okay? Whatever that may be. So when we look at this, this is measured in miles per hour, north, south, east, west. Miles per hour down Dodd. Miles an hour towards my house, okay? They can be any of those things. Miles an hour straight up, okay? The directionality becomes important there. They're both represented by V, okay? Speed and velocity are both represented as V. Now, we'll be pretty specific in our problems if we ask you for a velocity. But most of the time, you're going to see that we're going to just ask for speed, all right? Average speed, notice what happens to the variable. The average speed variable now is V with a bar on the top of it. That signifies average speed. Now, if you forget that part of it, that's okay. I'm not going to make a big deal out of this right now. But that's how we actually start to represent average speed. Some of you might put a V and then put the symbol AVE, average, underneath it. Absolutely fine. I'm okay with that too. All right. If we're looking for a change in velocity, then delta V. Again, that delta is that triangle. Triangle represents change for us. Is a variable that we'll use. That could be, hey, we're slowing down, so I'm going from 60 to 0. Or, hey, I'm going from 0 to 60, right? That would be a change in velocity for us. Okay. All right, now, how to determine the speed or velocity? So, since the speed is how fast we move, we ask the question, what is the difference between a car going 30 miles per hour and a car going 60 miles per hour? Besides the obvious that one's going faster than the other. Well, if we look at the numbers, 60 versus 30, what we're going to see here is 60 miles an hour should go further in an hour, right? So if all of a sudden you're driving down the road and you got somebody driving 30 and you got somebody driving 60, in 1 hour, you'll have traveled 60 miles. The other person, if they're going 30, will have traveled 30 miles an hour. All right? 60 miles an hour will take less time to cover a distance. What we mean by that is that if all of a sudden you're coming up to a stop sign going 60 miles an hour, you're going to have to stop earlier. At 30 miles an hour, guess what you're going to have to do? You can stop later on that thing. All right? You're going to cover that distance. When they talk about like texting and driving at 60 miles an hour, you're going to cover a substantial more amount of distance while your head is down, not paying attention to the road in front of you, than you would if you're going 30 miles an hour. Okay? So, if speed is related to distance and time, then here's our formula. So speed equals distance divided by time. So when we talk about miles per hour, that's miles divided by hours, feet per second, meters per second, right? Those are all distances divided by times for us, all right? So to find your average speed, this is the formula we want to use. You want to write this down. In the past, I've had people write this in the front of their notebooks. I've had people highlight, circle, star, arrow it, something just so that it stands out. I will put this on the front board so that you can see that when we get together for you B group of people, distance learners, just make sure you got it set up somewhere, okay? So what we see is V equals that delta D over T. Again, our velocity there or our speed there, miles per hour, meters per second, feet per second. Our distance is any one of our distance units, miles, feet, meters, centimeters, kilometers, anything like that. Time is anything. Seconds, days, weeks, months, years. Now, granted, we're not going to measure our car's speed in like miles per year, but you might measure some really slow stuff in that time frame, right? Like how slow does it take a glacier to move? Or how slow is molasses in January? Okay, that's stuff where we can use those different time pieces there. All right, try this problem out. Okay, so we got Piven Everson. All right, he drives his turbo and nitrous charged Honda Prius. Wait, I think a Prius is actually a Toyota. That's a little joke, by the way. In a local drag race. All right, he covers a quarter of a mile, 402.3 meters in 0.915 seconds. We want to know what his average speed is over that quarter mile. Now, as I start to look at this, what I want to do is I want to start to search for numbers and contextual clues, right? So if I look at that first sentence, it just gives me information. It doesn't really tell me anything about what's going on. The second sentence says he covers a quarter of a mile, 402.3 meters. Now that's a distance, all right? It then says in 0.915 seconds. That's the time, all right? So if I know those two things, those become incredibly crucial for me. So my average speed here then, well, average speed tells me if I know my delta D is 402.3, if I know my time is 0.915 seconds, I can find now my average speed, which is V. Notice I made a data table, all right? On quizzes, on tests, on stuff like that, on Schoology, you're going to be asked to place the values into the correct locations for your data table, all right? That'll typically be a drop and drag type of picture, all right? But for us, data tables become incredibly crucial because they tell us what we know and what we don't know. It also allows us to then look at equations and say, okay, I'm solving for V. What equation best matches this one? Well, the one that does is the only one we have. V equals delta D over T. All right, so now I start plugging in stuff. 402.3 is my distance, 0.915 is my seconds. I'm going to take that 402.3 divided by that 0.915, and what I find is that Piven's average speed is going to be about 440 meters per second. I don't do sig figs, but that being said, I will be specific and say, hey, round to 1 decimal, round to 2 decimal, round to 3 decimal. Okay? And then you also have to put a label at the end of that. That's going to be meters per second, m/s. All right? Just for a reference point, you're not going to ever have to be asked to do this. That's about 273 miles an hour. So that thing is moving pretty quick in order to get that quarter of a mile in under a second. All right? Like I said, you don't have to make that conversion. That just puts it in perspective how fast this thing is going. All right? If you got questions with that, zip me an email or kind of check out the next set of problems and stuff like that. Okay, so here's what I want you to do. This is practice 1-1. What I want you to do is pause the video right at this point in time. Get out a piece of scratch paper, go through each one of these problems, create a data table for it. So a V equals a delta D equals a T equals. Set up the problem and then find the answer. Because what I'll do after you're done pausing this and running these 3 problems is I'll show you the work and the solutions that I did. All right. So go ahead, pause the video for just a little bit here. And then once you're done running these 3 problems, go ahead, hit play again. And then what we'll do is we'll walk you through those. All right. So pause it for a bit and then we'll go. All right. Welcome back. Here we go. Number 1. On a spring break trip, you decide to go to Africa. You get into a staring match with an African elephant who takes your staring as a show of aggression and charges you. If the elephant is able to cover the 20 meters separating the two of you in 1.8 seconds, how fast is it going once it hits you? Again, the stuff we're looking for is we don't care about being in Africa. We don't care about the African elephant staring, seeing aggression. What we see is we've got 20 meters, right? That's going to be a distance. What else is happening? Covers that distance in 1.8 seconds. That's a time. We want to know how fast is speed, all right? So delta D, that's our first number, that's 20 meters. Our time that it took, 1.8 seconds. We're looking for our velocity. Now, again, when we start searching for formulas that match up to this, we have a distance, we have a time. There's really only one formula we can use, and that's V equals delta D over T. Notice, I got a little sloppy. I didn't carry the average velocity just because I care about the velocity at that point. Meaning, it went from 0 meters to 20 meters in 1.8 seconds. I just want to know at that instantaneous moment, at that time, after 1.8 seconds, how fast is it going? Okay, so I plug this in. 20 divided by 1.8 equals 11.1 meters per second. I think if I remember right, there's for every 1 meter per second, that's like 2.54 miles per hour. So this thing's traveling at about 26 or 27 miles per hour. All right. Full grown African elephant, those suckers move quick. You don't want to stare them down. All right. Now, something that I learned in college and that I did with my engineering professors, I boxed stuff. I may arrow it just to show you that that's the answer I want you to look at. Again, I wrote this 1-to-1 decimal point, 3 significant figures if you want to go back to the chem world and do that. But labels become important because that's a velocity that tells me that it's going meters per second. Okay. Number 2, you're touring Greenland when you decide to camp for the night. You camp below the Jakobshavn glacier. You set up camp and spend 12 hours at the campsite. If the average glacial speed of that glacier is 40 meters a day, which it actually is according to Google, what is the minimum distance you can camp away from the glacier before it engulfs your camp? This glacier is moving fast. All right. For glaciers, it's moving quick, I should say. Okay. So we see the time is 12 hours, right? That you set up camp, spend 12 hours there. We see the average speed is 40 meters per day. What we're looking for is how far away from this can we go? Now, there's a little bit of an issue with this one before we run. If you look at the timepieces on these two, the velocity is measured in meters per day, but the time is measured in hours. So we've got two options here. One's better than the other. We can change the velocity from meters per day to meters per hour. That one's a little tricky. So instead, I'm going to take that 12 hours and say, okay, how many days is that? Well, that's going to be about half a day. Okay, so 0.5 days. Now my times match up. Now this becomes a lot easier problem for me. So what I'm going to do, plug it into my equation. I know my 40 is my velocity. I know it's going to take half a day to get there. So my distance that this should cover, if I take 40 times 0.5, cross multiply, right? Should be, I can set this up at about 20 meters away. Okay, that's the minimum distance I can go. Now, to be fair, I'm probably doing at least 21 or more meters away from this thing, right? 20 meters is about 70 feet away from it that night before you decide to start sleeping there. Okay. Last one, Fast and the Furious announced a groundbreaking 15th movie in their series. I don't know how many movies they have. I just made that up. I think it's like 7 or 10 or something like that. Okay. This time it is all about the incredibly quick three-toed sloth. That's funny. They're not fast. Vin Diesel's modified sloth is able to travel at an average of 0.003 miles per hour. How many hours of filming sloth drag racing would it take Vin Diesel's sloth to cover the fabled quarter mile? 0.25 miles. All right. Now, if you see numbers and you're looking for numbers straight up, you see 15th. That doesn't mean anything. That's just a joke number in there, right? Three-toed sloth, again, doesn't matter to us. We see that speed or that velocity there is 0.003 miles per hour, right? We keep looking. We see the quarter mile. That's 0.25 miles. And then we ask, okay, how much time is this going to take? Because we're looking for time, we really only have one equation. The one equation is r delta v over dt, right? So we put our 0.003 equal to 0.25 over t. Now, be careful. This is the single most incorrectly solved problem. Not this specific one, but this type of one, where we have that t variable in the bottom. Okay? All of your intentions are good. All your math is usually pretty good until you hit this one. This one we mess up often. And by I mean my former physics students. You folks may be set solid golden with this thing, but my former physics students, this would be the killer problem for them. They would multiply the two across the top and get the complete wrong answer. Okay? So here's how we do it. We put the left side over 1. Okay? So now if you're looking at this, what you're able to see is I got 0.003 over 1 equals 0.25 over t. Now what I'm going to do is cross multiply and divide. All right, let's see if we can get some stuff here, right? So what I'm going to do is I'm going to cross those two, multiply that. And then I'm going to take that and divide. No, I did that wrong, didn't I? I said that wrong. Let me redo that, okay? Don't listen to that previous part. Let me clear this out. Khan Academy, that was not a good effort for my Khan Academy skills. All right? Here we go. Redo it again. Cross multiply. 0.25 times 1, right? We are then, so that's going to be our cross multiply. We are then going to divide whatever that sum is by that. Here's what it should look like, right? We should see 0.25 divided by 0.003. That thing should take 83.3 hours, all right? Sorry for the rust. I'm still working this out a little bit to myself, but that's kind of the 3 problems. If you got questions on any of those 3, zip me an email, let me know. All right, some clarity for 1-2. I'm sorry if it was confusing. This lab is due on Friday, so if you haven't finished it up yet, you're absolutely fine. If you haven't gotten to it yet, you're absolutely fine. If you've got more questions and you want to wait until Thursday B group to see me in class, then let's do it. If you're a distance learning person, zip me something on Wednesday and we'll figure out how to get through this. Okay. Your graph should be the distance on the x-axis, and then on the y-axis there should be the average time for each distance. So what you're going to see is you should have two different lines, one for one object, one for the other object. And then you're going to draw two lines of best fit. Now, please make sure your lines of best fit are hitting as many points as you can. It can be a straight line or it could be a curved line. I just don't want to see jaggedness in it. All right. Graphs need to be added to your section of lab underneath there. If you worked with other people, take a picture, have them share it with you. If you work just by yourself, snap a photo of that lab from that separate sheet and just attach it, and then just insert that image there. All right. Do make sure you get a picture of lab setup. Otherwise, tomorrow on Wednesday, what we'll do is we'll talk through, and you'll have a little iPad activity just to get used to how you work some of those apps on there. So if you have questions with any of this lab stuff or any of the V equals delta D over T, please don't hesitate to shoot me an email. Okay. Otherwise, that's kind of it for the day. So finish up whatever labs you have, and if you want to submit them today, great. If you want to wait until later on, absolutely fine as well. All right. Otherwise, hey, have a great rest of your day, and hope to see you soon. Take care.